In this video, we're going to work with what's called the definite integral. Now, in Riemann sums, which was the last video, we were talking about taking a bunch of little bitty tiny baby rectangles and finding the area underneath a curve. And then at the very end of the video, I sort of gave a preview of what a definite integral is, but there are indefinite integrals where there's no limits, upper and lower bounds on the integral sign. And then there are definite integrals where you have normally something like we're going to integrate from 0 to 5 or 2 to 16 or a to b, 0 to t, something like that. So if you have values or even variables, on the lower and upper portion of the integral, then that's a definite integral. Okay, so what we had started off with in the Riemann sums as a bridge to here is we have this definition. Let's look right here where we have the limit, right? And these little double bars with that delta x is talking about, we mentioned about how you have the widest section of the partition, the widest width of the rectangle. And as you make the widest rectangle go to 0, and then the next widest one goes to 0, and the next widest one goes to 0. So all of these rectangles that you have right here, sketched in here, the widest one would go to 0, and then the next one, and the next one, and the next one. And remember, these are your y values, and this, which was your height. And then this delta x was your base. So you have your base times your height, and then you're going to add them all up, right? So this is your base, this is your height. Multiply them together, add them all up, and now you have the area underneath a curve. And this is used symbolically as you're going to integrate this function, whatever this function is. This one happens to be 6x. And you're going to integrate it from some lower bound a to some upper bound b. And this then becomes this fundamental theorem of calculus because it's fundamental to everything. All right. So we've been building up this whole time, all the way through this Calc 1 base course to get to this point. So this is a fundamental theorem that is going to serve you well through the rest of everything you're going to do for your calculus series and in all of your courses that use calculus, like physics and math, of course, your future math classes, and engineering, and you name it. If it uses calculus in business math, okay, then you're going to have to do this. So the definition is, if you're going to integrate from a to b f of x dx, then this capital F says take the resulting integral of the original function, evaluate it at b, and then subtract the resulting integral function and evaluate it at a. So you always go b minus a. All right. So if this is kind of like, huh? Go back to the Riemann sums, which is the previous video, and look through that, and maybe it'll make a little bit more sense. All right. So again, trying to kind of bridge the gap, between Riemann sums and here. If what we were trying to do is this is the y is equal to 6x line. And if what we wanted to do was to find the area, not from 0 to 6, but let's say from 3 to 5. Okay, so this would go, if I could draw a straight line, all the way up here. And here's 3. All right, so I really just want this section. Okay, now if we were going to do that section, I guess this is 5 right here. Didn't have to do that at all, did I? So here's 5 all the way up to there, just so that we have an agreement here. And here's 3. We're going to draw it to scale, goes up to This would be 18. All right, so here we go. It's much easier when you can just sketch things in algebra without having to have a graph, which makes you honest and have to redo it so it looks right. All right, if we just wanted to go from 3 to 5, then what we would have done in geometry class, let's say, is you would go from 0 to 5, and if this y is equal to 6x line, then this would be 30, right? So you would find the area of the large triangle, which would be 1/2 the base times the height. And then you would subtract out the smaller triangle over here and 1/2. And if you're going to go here, that's the base times the height, which is 18. And this would give you 48. Okay? So that's what it is based on geometry. But let's try and see what happens if we do a definite integral. So I know the function that I used was y is equal to 6x. So 6x goes right here. Keep in mind that just like mentioned in Riemann sums, if this is an x, it wins. So you can't have y dx and then try to integrate y. If this is an x, this has to be an x. So y is equal to 6x, so that goes there. And we want to find the section from 3 to 5. Okay? Now you treat this like you did when you had an indefinite integral. You use all of your rules. You know, do you have a power rule? Is it a function that you would recognize like a trig or hyperbolic or e function or something like that? So this is a power rule. So you have your 6, you add 1 to the power, divide by the new power. But instead of doing plus c, because if what you had was not the 3 and not the 5, this would be an indefinite integral, and you would go plus c. Okay? However, what we had was a definite integral from 3 to 5. So what we're going to do is to evaluate this, and they usually show it with a little straight line right here, and they'll say we're going to evaluate this from 3 to 5. Right. Now, this can look like all sorts of things. Sometimes people will go, all right, we're going to do 6x squared over 2, and they'll just sort of use the parentheses as part of the 3 to 5, or they'll use squared off brackets from 3 to 5. So just sort of follow what your teacher is demonstrating for you, or if you just have a book, use what's in the book so you'll have some reinforcement. But the straight line is probably the most common. So this is actually 3x squared from 3 to 5. And what you do is you put the 5 in here first, and then you always subtract, and then you put the 3 in. So you go 3 times 3 squared. So 3 times 5 squared, 5 squared is 25, 3 squared is 9, so you would have 3 times 16, and this is 48, which is exactly what we got over here. Okay, so I just wanted to show you a simple one so that you can kind of see that, okay, it does seem to at least work on a triangle, right? And we've proven all this, you know, going back into the indefinite integrals and so forth. So, you know, go back and check that. Now, okay, let's talk for just a second. So when you go into these tests, and unlike what happens in a lot of courses in my experience, and I have to say that when I was a young student in high school, I did this myself, which is I'd get out of a class and I'd go, oh, thank goodness that's over. And you sort of do this mental erase and go, and now I can relax. All right. Now the problem with that is that if you do that and you don't need that information, it may not be a problem, at least at the moment. But for calculus, if you're taking calculus 1, I'd say well over 90% of the time, you're going on to something that uses that calc 1 routinely, right? So you cannot forget any of this, right? So you have to find a way to store all this and to keep it accessible, right? So when you're going in for the test or whether you're getting ready for your next semester, and trust me, I know teachers who in Calc 2 first day of class throw down a piece of paper and go, "It's a test." And then they expect you to be able to do Calc 1 the first day of Calc 2. So you can't forget these things no matter how long a break is between your Calc 1 and Calc 2 class. So let's kind of think. Hopefully you've been making kind of lists as we've gone through this course. So you go, well, okay, how many things can I integrate? I mean, what do I know? You know the power rule, right? You add 1 to the power, divide by the new power. Okay, you know if it's something like x to the minus 1 and you're going to integrate that and you go, well, let's see, what did I take the derivative of to get x to the minus 1? Because if you add 1 to that power, you get 0. And then when you divide by 0, that's a problem. All right. So you know the power rule. You know certain patterns, like an x to the minus 1. You know how to integrate trig and with sines and cosines and secant squareds and so forth. Those are patterns. There's patterns that go with the hyperbolics and the inverse trig functions. So there's a good chunk of patterns, and you have to be familiar with those in order to recognize the pattern that it came from, okay, and the power rule. And that's pretty much all you got. And then you have the substitution rule that says maybe I could get it to look like one of those patterns or to look like the power rule. So when you get on the test or something, you look at it and go, oh, I'd really like it to be a power rule, okay? And you go, that's really kind of what I need. All right, so you just sort of have to work your way through that, and then keep telling yourself that, okay, it has to be a pattern I've seen, or maybe if I think about it enough, I get to a pattern I've seen. So you just sort of have to keep telling yourself, this is going to work, this is going to work. So what happens if I wanted to integrate from 1 to 4, x minus 6x plus 3x to the minus 1 dx? Now, I just want to kind of gradually build you through these. So you go, okay, this looks like it's going to be power rule, right? Because I've got a series of terms, with powers more or less in it. So you add 1 to the power, divide by the new power. I guess really if I'm going to add this x and this minus 6x, I could say it's minus 5x. And integrate that. That would be legal, wouldn't it? And yes, it is. All right. So it's supposed to be plus, but it doesn't look like it. All right. Here we go. So I have minus 5, add 1 to the power, divide by the new power. Now, like I mentioned just a minute ago, if you take this 3x to the minus 1 and you add 1 to the power, you'd have 0. And then when you divide by the new power, you would be dividing by 0, and that's illegal, undefined, right? So you have to sit here and go, there must have been a pattern, something that I took the derivative of and got an x to the minus 1. And if you remember, the derivative of the natural log of x is 1 over x, right? So this says, what did you take the derivative of to get to this? Because what you're saying is this right in here is the derivative of something. And what you're trying to do is to retrieve what that something was. Okay? So this is what that something was, and I'm going to evaluate it from 1 to 4. All right? So what you have to do is to say, all right, I'm going to, everywhere I see an x, I'm going to put in a 4. And then I'm going to subtract, and everywhere I see an x, I'm going to put in a 1. All right, so when you clean this up, you're going to get minus 40 plus 3 ln 4 minus, this is a minus is a plus, 5 halves, minus 3 ln Okay, so this turns out to be, let's see, we need a common denominator for the minus 40 and the 5 halves. So minus 80 halves plus 5 halves. Let's group the natural log ones together. Teaching you bad habits by being messy with my natural log. All right, so this turns out to be negative 75 halves. And this 3 is actually a power for here. Remember your natural log rules, right? So you have the natural log of 4 cubed minus, and this 3 goes up here, the natural log of 1 cubed, and of course 1 cubed is just 1. So you have negative 75 over 2 plus natural log. And do you remember if you were subtracting natural or any log, okay, of the same base, that if you're subtracting, you can combine them into a single logarithm by dividing. So this would be 4 cubed is 64 divided by 1, which is just 64. So this is minus 75 halves plus the natural log of 64, which if your teacher wanted you to approximate it, you could. And I'm going to remember the original one had it x minus 6x. So technically, if you write it in the simplified version, I know, I'm not one of them, but I know some teachers who will take off. Hopefully you know how your teacher is, all right, by this point. All right. Now, so what we're trying to do is to try to figure out how to get things into the power rule if at all possible, because it's pretty much straightforward. So if you had something like the integral of y plus 1 dy, because they don't always have to be x's. Now, so if you have this, again, if this is a dy, everybody else has to be a y, so everybody is. And so we're going to go from negative 3 to negative 2. And so you can have negative numbers on your upper and lower boundaries. This is the lower one. There's things you can do if that's not the lower one, and by lower I mean the left one, and this is the one to the right. Now, we don't have a reversal for the product rule, so what we have is the power rule and patterns, all right? So some of you may be going, oh, I could make u be y plus 1, but if you make u be y plus 1, then what do you do with this extra y that's out here? There's a way to kind of work around that, but let's try not to make it any more complicated than it has to be. So what we could do is if we have something that looks like I could multiply it out, well, let's just do that. So when you're looking at your test, I have a kind of a list of order of what I'm going to do. I look at it and go, okay, is it the power rule? And then I go, okay, can I make it be the power rule? Okay. And if not, then I start looking for patterns, or then can I use u? So don't just jump in and assume you're going to use the u substitution. Kind of have a list that you just sort of check off as you go so you don't miss anything, right? So then first you have to integrate. Okay, so you're saying I took the derivative of something and I got y squared plus y. What was it? Well, to reverse it, you add 1 to the power divided by the new power. And this would be y squared over 2. And what you're going to do is to evaluate it from minus 3 to minus 2. So what you do is you're going to put minus 2 in everywhere you see a y. And then you subtract. And then everywhere you were, you're going to replace the y's with a minus 3. Okay. Now, be careful with your signs. All right. If you have a habit of dropping negative signs, you need to slow down a lot in this section. So be really careful, right? So when you clean this up, you get minus 8 thirds. This would be 4 halves, which is 2. this is, okay, this minus times this minus, because a negative cubed is still negative, so you'd have plus and 27/3, which is 9 last time I checked. And then this minus goes all the way over here. Negative 3 squared is positive, and then you multiply it by a negative, and you get this, right? So these can, you can do the hard part really well, and then mess up with just your plus and minus signs, and it's gonna get you. All right, so slow down. So I have a tendency to sort of group things together. So I'll sit here and go, all right, so these are thirds and these are halves. So that way I can kind of watch my math a little bit, because, like, I'm human, and every once in a while I make a mistake, and every once in a while you will too. So now I need 6. So I have 38/6 minus 15/6. And when you do these, you will discover really quickly where you can shave off time and cut some corners. Um, I can shave off time sometimes, getting common denominators in my head or whatever, not with a negative sign. So be careful. You have to do enough of these to figure out what it is you need for yourself to be accurate. Because where you're accurate is not going to be the same as someone else's. All right. How about this one? All right. Now, this one, because it's a monomial on the bottom, and that means there's just one term, because there is a monomial on the bottom, you can split it up and say this is x squared over x to the 3/2 minus 1 over x to the 3/2 dx. All right. If you had something that looked like x squared, let's say plus 2 over x squared plus 1, this would be a binomial on the bottom, and you can't split this x squared plus 1 and make it be x squared, and this is 1. Now, there's a way to separate out non-monomials in the bottom. They call it partial fractions. It's a whole nother technique, right? But what you could do is something like, oh, you could go, well, look, hey, x squared plus 2 is x squared plus 1 plus 1, right? So I could say x squared plus 1 over the entire binomial, right? Plus 1 over the entire binomial. So you can repeat the entire binomial or polynomial as many times as you want. You can separate these, but you have to repeat the denominator over and over and over. Okay, you cannot separate the denominator into pieces and parts without partial fractions. So if it's x to the 3/2, you just repeat the denominator. Okay, if it's x squared plus 1, you repeat the exact denominator. Now we're going to see if we can clean it up. So I have not integrated yet. So x squared over x to the 3/2, you would start with the top power and subtract the bottom power. So this is x to the 1/2 minus, and then I don't have anything to work with on the numerator, so this is x to the minus 3/2 dx. All right, so now I'm ready to integrate. So I add 1 to the power. Dividing by 3/2 is the same thing as multiplying by 2/3, so you just flip it and write it down next to it. Minus. So then you have x. You add 1 to the power, so that'd be negative 1/2 now, because you added 2 halves. And then to divide by negative 2 halves is the same thing as to multiply by its reciprocal. So this is going to be 2 over 1, right? So you'd have 1, 2. This is a negative. So this is kind of complicated. Do you see what happened? So I added 1 to the power, got negative 1/2. And to divide by negative 1/2 is something divided by negative 1/2 is that something times negative 2, right? Okay. Now this negative and this negative are going to see each other, and you're going to have to work with that, right? And we're going to try to evaluate this from 1 to 9. Okay, so I have, this is going to be 2/3, so I have 2/3. I put 9 in there to the 3/2, and this minus makes plus 2. Put the 9 in there to the minus 1/2. Now that's just the 9. And then I'm going to subtract 2/3, put the 1 in there, plus 2, put the 1 in there. Sometimes it helps if you have a specific set or type of parentheses you're doing between, this is evaluating it at 9 and this is evaluating it at 1. So I have always got a tendency, if I can, to use these squared ones to say this, I'm moving from one to the other so I don't get lost. Visual clues will help you to stay on task, right? So then we clean this up. And so this is 2/3, and you work from the bottom up, right? So this is the square root of 9. So the square root of 9 is 3. 3 cubed is 27. Plus 2, the square root of 9 is 3. And then it wants a negative power of it, so it's 1/3. Minus, okay, 1 to any power is 1, right? So you got minus 2/3 plus 2. Okay, so this is 18 plus 2/3 minus 2/3 minus 2. So see how sometimes it helps to not try to clean up all of this and then clean up all of this. Sometimes they work with each other, right? So 18 minus 2 is 16. So this is the integral from 1 to 9 of x squared minus 1 over x to the 3/2 dx. Okay, this is already like half an hour in. This is going to be a long video, but it's well worth its time. All right, let's try this one. 0 to 2 of 2 to the x plus 6 dx. Now, some patterns are a little more obscure than others. Remember that the integral of e to the x is e to the x, just like the derivative of e to the u is e to the u du, right? But we had another one that says if you have some base besides e, and they call it some base a raised to some variable, then when you integrate it, you get a to the x over ln a. So here we go. So I'm going to go ahead and integrate 2 to the x. So that a is 2. So I'd have 2 to the x over ln 2 based on that little property plus 6x evaluated from 0 to 2. So we have 2 to the second power over ln 2 plus 6 times 2. And some people really quickly and erroneously get the idea that if 0 is down there, then this second part is always going to be 0. And I'd say most of the time it is, but not always. And so if you think it is, you're going to get caught because teachers like to put that in there to make sure you're paying attention, right? So this is 2 to the 0 over ln 2. We're really, we're just really trying to make sure you have all the little details down before you move on to the next class. All right. Or use it in some real life application where it's actually your job or somebody else's life, depending on you paying attention to details. And so we teach you to pay attention to details now so that you pay attention to details on the job. Okay. All right. Well, 6 times 0 is 0, but 2 to the 0 power is not 0. Anything to the 0 power is 1. So you have 1 over the natural log of 2. And so this is 4 over the natural log of 2 plus 12. Now, if I have 4 and they have the same common base of the natural log of 2, this would be 3 over the natural log of 2 plus 12, which is an exact answer if your teacher wants you to approximate it to a certain point. You can also use your calculator to do integrals like this. I'm not going to show it to you though, because if your teacher wants you to do it, they'll show you, right? The other thing is that some of the tests you take in the future for certification or whatever, they'll let you use a non-graphing calculator, which doesn't, of course, and then if you don't have a graphing calculator, it won't necessarily do integrals. So you need to know how to do these by hand. And depending on your teacher, we want, and I'm one of those, we want to verify that your algebra skills have not suffered since you did them. And that's important, right? Now, it doesn't always have to be an x. We had y, now we have theta. So but this is like if you just have e to the x, it's not e to the 2x or e to the 4 theta. This is just simple. So when you integrate it, you get e to the theta again. And what did you take the derivative of to get a positive sign? Well, it must have been a negative cosine. And we're going to evaluate that from pi to 2 pi. So we would have e to the 2 pi minus cosine of 2 pi minus e to the pi minus cosine of pi. So this is e to the 2 pi minus cosine of 2 pi is 1, right? And this minus is going to distribute. So you'd have minus e to the pi plus, and cosine of pi is negative 1. So you have e to the 2 pi minus e to the pi minus 2. And you could, try to manipulate this, factoring out e to the pi out of the first two terms or something. And if they want you to approximate it, you can, but we're going to leave it right there. Alrighty. So then let's do another trig one. Now, what you can do is to factor out these multipliers. And the question is, because this is not the power rule, is what did you take the derivative of to get secant theta tangent theta? Well, that would have been secant theta, right? And then we're going to evaluate this from negative pi over 3 to pi over 3. So you have 6 times secant of pi over 3 minus secant of negative pi over 3. So this turns out to be 6 times 2 minus 2. So this turns out to be 0. Okay. Now, so far they've all just been nice x's or thetas or y's, but we haven't had like 4 theta plus 1, sine of 4 theta plus 1, something that would require u. So let's try this. and kind of get into the mindset. All right. Now, there's two ways, or three ways. There's actually three ways to do this. One way actually has two variations of the three, and then there's another way. So one thing you could do, because when you look at a problem in math, the reason I liked math so much was because if you really don't relate to what they're asking in that format, or you just don't like that format, if you can manipulate it into something else, and you're allowed to do that, then maybe you can make it something you're more comfortable with or that you're more proficient with. So one thing you could do is to sit there and multiply out this y minus 1 3 times. If this is, if you've forgotten how this works and you're like, oh my gosh, this is 20 points on the test, I can't leave this blank, then you're going to go through all this work and multiply that out. And when you get it done, you would have y cubed minus 3y squared plus 3y minus 1. Now I skipped a bunch of steps. dy. And then you would have y to the fourth over 4 minus y cubed plus 3y squared over 2 minus y from minus 2 to 2, right? And then you would substitute that in there and then subtract that out. And by the time you get done, you'd have minus 20. Now I skipped, there's a whole big section in here of multiplying out, and I skipped a couple of steps in between here, but you would get minus 20. Right, now let's see what happens if we use that u to u thing. So we go, well, I really like it to be just something raised to the third power, and then I could make life real simple. So let's see if u would work. So if u is my minus 1, which is that inside part, the derivative, okay, with respect to y would be 1, right? So du, it's supposed to be y, not x, is 1 dy. Okay, well, I've got an understood 1 dy right here. So this is du, and this is u cubed, right? Now, I need you to stop whatever you're doing. So a lot of people watch these and watch TV, listen to music. I watch the people that go by the window, whatever's going on. But this is terribly important, and I really need you to concentrate on this. So in the past, what we did is we went, okay, we're going to integrate u cubed du, right? And then we would add 1 to the power, divide by the new power, correct? Okay. And then we'd either go plus c or whatever we're doing. But in this case, we're doing a definite integral, and I need you to be really clear about something. Okay, so if you put minus 2 to 2 right here, and if you say we're going to evaluate this from minus 2 to 2, I need you to stop and listen to what I'm saying. Okay, if this is a dy right here, these have to be y, which they are, okay? But these are also y's. So these are y values, okay? So in here you have u cubed du, but this and this are y values still. So you cannot substitute this 2 right here and this minus 2 in to a u, all right? Because they're not u's, they're y's. So this is where you really have to explore this enough to where you know what it is that you want to do. Some students will just leave these off, okay? And I have to admit that when I'm doing myself, for my own self, not for demonstrating for the students or anything, I just have a tendency to leave them off so that I'm not tempted, okay? So that I would leave this off as well, and then when I get to the fourth, I'm over 4, right? I'm still not tempted, okay? And so then you go, wait, I need to change u back to y, okay? So u is y minus 1. So you have y minus 1 to the fourth over 4, right? And now I'm going to evaluate it from -2 to 2. So some people just drop off these upper and lower limits so that they're not tempted. Okay. But then they forget sometimes to put them back, and they'll end up with a plus C, or no plus C and no number either. All right. So you need to figure out your strategy and the way you want to denote it so that you remember, do not substitute a y value into u. Okay. So then you would go, all right, so then I would have you substitute in 2, and then substitute into -2. And this would be 1/4 minus, okay, -3 to the 4th is 81. So you would have 81/4. So this is -80/4, which is -20, which is that same thing we would have gotten over here. Right. Now, there is another way to do these. This is the variation of the u substitution. So remember we had said u is equal to y minus 1? All right. So hold on to this thought right here. And then let's go back to where we just were saying, all right, what happens if we had u cubed du? We would add 1 to the power and divide by the new power, right? That's this part right up there. See? All right. Now you cannot substitute a y value into u, but you could substitute a u value, right? So watch what happens. If u is equal to y minus 1, and we had y was equal to -2, because remember we had a -2 here and a 2 there, even though they were y values, right? So if y is -2, u is -2 minus 1, right? We're going to substitute it in here. So u is -3. So this -2 becomes a -3. You okay? And then for the upper limit where y was 2, u, okay, we're going to substitute y in right here, is 2 minus 1. So u is 1. So this becomes a 1. And these values are u values. So now we've gone from these are y's to these are u's. And we can substitute a u value into u. So what we would do is to substitute 1 in there. And then we would subtract, and we would substitute a -3 in there. So I would have 1/4 minus 81/4. And this is -80/4, which is -20. So see how we got the same answer? All these 3 ways. So unless your teacher requires you to do a particular method, they don't really actually care which way you get it done. Okay? Other than, obviously can't cheat off somebody. All right. So let's try another one. What if we want to go 0 to power 6 of cosine x dx over 1 plus 3 sine x? Now, obviously this one is not a pattern. This is 2 different things working against each other or working together to try to support a coordinated effort. But when you're trying to figure out which one's u, because u could be cosine x, or u could be 1 plus 3 sine x, or maybe 3 sine x, or whatever, then you normally pick the more complicated one. And 1 plus 3 sine x is more complicated than cosine x. And I'm going to flip it around a little bit and make it 3 sine x plus 1. So du dx is 3 cosine x. So du is 3 cosine x dx. And you've got cosine x, you just don't have a 3. So you could put a 3 in here and then undo it. So this would be 1/3. And what you would have is, because this right here is your du, and this down here is your u. So what you're going to do is to try to integrate u to the -1 dx, or du. Sorry about that. All right. So this would be 1/3 the natural log of u. And we originally had 0 to pi over 6, but keep in mind, these are x values, and you have u. So we have 1/3 the natural log of 3 sine x plus 1, because that's what u was. And now you can evaluate it at these x values. So you have 1/3, and you have the natural log of 3 sine of pi over 6 plus 1 minus the natural log of 3 sine of 0 plus 1. Okay. All right. So the reason I wanted to do this one is just to remind you of some of the tricks you can do. So again, if you're subtracting, you can actually say it's this first one divided by the second. So you would have the natural log. Now you can't cancel, right, these signs because they're not the same. So you would have 3 sine of pi over 6 is 1/2 plus 1 over 3 times 0 plus 1. You can't cancel the ones, y'all. Okay, 1/3. All right, natural log. All right, 3 times 1/2 is 3/2 plus 1 is 5/2. So this is 5/2 over 3 times 0 is 0 plus 1 is 1. So this is 1/3 the natural log of 5/2. And this is 0 to pi over 6 cosine x dx over 1 plus 3 sine x. Now, keep in mind what we just did. Let's go back up here. So right here, where we had 1/3 natural log of u. Now, we couldn't utilize the pi over 6 into the u because that's an x, and we needed to know the other thing. So I'm going to squeeze this into the space right here. If we know that u is equal to 3 sine x plus 1, if x is pi over 6, u would be 3 sine pi over 6 plus 1, so u would be 5/2. And if x was 0, u would be 3 sine 0 plus 1, so u would be 1. So you could evaluate this from 1 to 5/2, right? So this would be 1/3 the natural log of 5/2 minus the natural log of 1. And the natural log of 1 says, what do you take the natural log of to get 1? Okay, so this is, I'm sorry. Okay, so this is, let me rephrase what I just said because I think I said it wrong. Okay, so this is e to what power? Let's put a little question mark there. Is 1. Okay, so what is it that you need there in order to get a 1? This would be 0. Okay, so this is 0. So this is 1/3 natural log of 5/2. And I don't know about you. I shouldn't say things like that since we're dealing with the letter U. I don't know how y'all are doing. Let's do Southern y'all. All right. So I don't know how y'all are doing, but the this little part right here, we sort of diverge and say, okay, let me figure out what the U limits are. Okay, the upper and lower limits, so that I can do this. This took a lot less space and worrisome and chances for me to mess up than to do all of this right there. So sometimes it's helpful to go ahead and change it to U and sometimes it's not. Okay, now, so let's try a problem really quickly. Well, actually, let's just think about a problem here really quickly. So if you had something, fairly simple like, let me make one up. Sine of x plus cosine of x. Oh, let's be crazy. Let's do this. Dx. All right, I'm just making this up. All right, now, if before you get crazy and try to do all sorts of stuff like, oh my gosh, which one's u and du and everything, doesn't sine squared x plus cosine squared x look kind of familiar to you from trig? And this is usually the one that people hang on to the longest, I think, because it's kind of cute. All right, well, sine squared x plus cosine squared x is actually just 1, right? All right, and what happens when you try to integrate 1? Well, it's just an x. Agreed? And I didn't have any limits of integration. It's not like they said -1 to 2 or anything else like that. So am I done? And if you said yes, you're wrong. So remember, if it's an indefinite integral, you have to do the plus c. So if you said I wasn't through, and don't forget the plus c, yay for you. And if you said, I think you're done, well, I would have taken 2 points off on your test if you'd stopped there. So keep in mind that typically on this test, they mix indefinite integrals and definite integrals in at the same time. So you have to keep track of, are you doing plus c or not, all right? And don't lose track of trying to get it a little bit simpler before you get crazy and try to do the more difficult things before you get too busy, all right? Now, there was one I wanted to do. All right, let's do this one. So all the way up here at the top, I have a drawing. If I can get all the way up to the top. We've been working for a while. Here you go. Okay, so if you have to do something with an absolute value, like this one, x minus 3 dx. So we don't have a pattern for what do you do with an absolute value. We probably haven't even done one. So I drew it for you. All right, so this is the absolute value that's been moved to the right 3. So here's 3. All right, and as you can tell, this has a distinct sudden jump. Okay, if you're talking about limits, from both sides. On the right, it has a positive slope. On the left, it has a negative slope. So this part right here, you can kind of think of it as a partial of y is equal to x minus 3, right? And this one over here actually is the negative of x minus 3. I don't know if you believe that or not. Do you remember from algebra class, they had the definition of absolute value is x if x is greater than 0, and it's the opposite of x if x is less than 0, right? And it kind of goes like based on the original absolute value that goes right here. All right. So if you're to the right, you're going to get positives because you have a positive in there. If you're to the left, you're still going to get a positive, but you have to do the opposite of what the number is for x on the left. So what you have to do if you have an absolute value sign is I would suggest that you graph it. And then this portion that's positive is just the function that was in there. And this portion on the left that slopes down is the negative of what you had in there, right? Well, then what you have to do is, since you have 2 different equations, you have to break this into 2 different sections, right? So you would have the section from -1 to 3 of the negative of x minus 3 dx. And then you would have the section from 3 to 5 of x minus 3 dx. See? So from 3 to 5 is this section. And I only want to go from -1 to here for this section. Okay? So we're going to try to clean this up as best we can. And no one's going to remind you to do that. All right? So you just sort of have to add that to your list of patterns, recognizable patterns if you have absolute values. So you would go, well, okay, I'm going to try to make my life as simple as possible. So I'm going to factor this negative out into the front. So I'd have negative and -1 to 3 of x minus 3 dx plus 3 to 5 of x minus 3 dx. So this is the negative of x squared over 2 minus 3x evaluated from -1 to 3 plus, same thing, x squared over 2 minus 3x from 3 to 5. So you would have the negative, I'll try to hurry this up a little bit, 3 squared over 2 minus 3 times 3 minus a -1 squared over 2 minus 3 times a -1. Now, I don't know about you, but there's a lot of negatives going on in here, and you may already be going, wait, are we losing one? Yes, we kind of are. This one applies to all of that. So this says the negative applies to the integral evaluated at 3 minus the integral evaluated at -1 plus. So then we would have, I like to have a pattern where they look the same so I kind of know what I'm doing. Okay, because I don't know about you, but sometimes when these things get crazy busy, it's like, wait, where was I? Did I just drop something? Hopefully not. I meant that as in thinking about it, not that I'm actually wondering if I dropped something. Hopefully I didn't. But I like seeing these patterns, where I can kind of keep my mind on where I'm at in this process. So when you clean this all up, and I often wonder if y'all actually want to see all this math. I'm assuming if you're watching these videos, you're kind of overwhelmed, maybe, in your class, and perhaps seeing all the math worked out will help you to kind of be able to cope a little bit longer. All right, so then you'd have the negative of 8 halves minus 12 plus 16 halves minus 6, which turns out to be 10. All that work for 10. I mean, you kind of want it to be something really horrible so that you feel like it was worth all that work to get there. I think the only thing that would be more frustrating is if it ended up being 0 and then you'd be going, okay, I did all that work to get 0. Okay. Now, speaking of absolute values, sometimes you don't have to do it quite like that. If you had the absolute value of sine x, for example, it might help you to kind of think about the image of whatever it is you're integrating. Normally sine goes like this. Okay. But if you're going to do the absolute value of sine, then what it's saying is all of these parts here that are dipped down in the negative area, they're going to flip up. So you'd have this original part that was up there, and then this part's going to flip. So this is going to be up here, and then the original part, and then this part's going to flip. So sometimes you can use the geometry of the drawing to figure out what to do. Because since this area is equal to this area, but this one's positive and this one's negative, you could just find this area and then use it however many times they're asking you to do it. All right. Now, hope that made sense. Maybe I'll put one of those on the little worksheet. Remember, there's a worksheet in the description, where you can do some problems and I work them out. I'll try to remember to put one like that in there. All right. Now, these are all the other patterns for the inverse tangents and secants and inverse trig and hyperbolic sines and cosines and tangents and inverse hyperbolic whatevers. All right, so let's try a couple of these. Won't go into just way too crazy, right? So let's try something that goes like the integral from 0 to the square root of 3 over 2 of 1 over 1 plus 4x squared dx. Sometimes they put the dx up there in the top and it just looks like this. And I have to admit that when I was first learning calculus and everything, it just kind of unnerved me when the dx was up there. So I just would take it and drop the dx over to the side like this and put the 1 up there because that sort of made me a little bit more in my comfort zone. And to be, anything that makes you more in your comfort zone makes your brain work a little bit smoother. All right. So we look at this and we're going, okay, great. It can't be that u to u thing, okay, because I kind of resist going to these uh, various forms of inverses and hyperbolics and everything if I don't have to. So if you went, okay, what if u was 1 plus 4x squared, then du would be 8x dx. And even though 8's not a problem, you can get an 8, you just put a 1/8 in the front. I don't have an x, okay, an extra x, so I can't use that. So then you go, great, maybe it's one of these because obviously it's not the hyperbolic sines and cosines, these because they don't have x's and 1's in them. But once you see something that's like 1 plus something, or especially if there's a square root down there, and you can get a 1, and sometimes you can factor it to where it becomes a 1, it's probably one of these. Now, your course may not have these inverse trig and these hyperbolic and inverse hyperbolics. So if your course does not have these, you can quit watching this tape. This tape. Oh my gosh. How old am I? All right. You can stop watching this video now because this is what we're going to end up doing. Just a few of these and be done. So if you don't have these in your course, you could stop now because this is what the rest of the video is. All right. So here we go. So I'm looking for something that does not have a square root and it's got 1 plus something squared. I don't know. Okay, do you see anything that looks likely? Right, this is as close as I can get. It looks like it's of this form, right? So I think it's going to be an inverse tangent. All right, so we would have, to get it more into that form, it'd be 1 over 1 plus, because this says whatever it is that you're squaring, it has to square the whole thing. So this would be 2x squared. So u is 2x. So du is 2 dx, right? So there's my dx. So what I need is a 2. So what I would like to have is a 2 right here. And I can do that if I multiply by a 1/2 to undo it. Okay? So this is 1/2 0 square root of 3 over 2. All right. And this is 1 over 1 plus u squared du. Right? So this is 1/2. Now, this would be the inverse tangent of u. And now, keep in mind, these are x values. And you cannot sub an x value into u. Now, you could transform these x values into u values, right? But I'm not going to do that right now, right? So what you would then have is 1/2 inverse tangent, and u was 2x 0 to square root of 3 over 2. That's not too bad, right? So you just change it back to the original variable that you had, and now you can substitute those in. So you have the inverse or arctangent of 2 times the square root of 3 over 2. You substitute that in for x minus the inverse tangent, or if you say arctan, the same thing. Okay, so this is 1/2. And this 2 cancels this 2. And the arctan or inverse tangent of square root of 3 says, what angle did you take the tangent of to get the square root of 3? Now, granted, there's multiples as you go around the circle and, unit circle and everything. But again, these are limited for these inverse tangents, depending on whether you're working with sine or cosine or whatever. Sine was limited to these quadrant 4 and quadrant 1. Tangent is limited to this, right? Because we're trying to make a one-to-one function from an infinite domain. Well, tangent has breaks in it, but you get the idea. Something that repeats infinitely, right? So this one has to be pi over 3. Okay, minus, and what do you take the tangent of to get 0? That would be 0. So this is pi over 6. So 0 to square root of 3 over 2, 1 over 1 plus 4x squared dx is pi over 6. Okay, so what if we want to do from 2 to 4 dx over the square root of x squared minus 1? All right, so I'm looking for something that's the square root of x squared minus 1. Now this is x squared minus 1, but it's got a negative right there. Here's an x squared minus 1 that doesn't have a negative. Let's do that one. Okay, so this would be the inverse hyperbolic cosine. So this would be the inverse hyperbolic cosine from 2 to 4. So this is now this is the exact answer because, and I hate to say it, but usually when you have an exact answer, a lot of times, it doesn't strike you as a number. Is that like, you want to sit there and go, is this like a huge number? Is it a small number? Is it like closer to 0, closer to 1? It's like, I'm not real sure what that number would represent. And so what you could do, you would have to go look this up because I kind of doubt that you might know this one. This is how you evaluate these. I don't know that you're responsible for this. This is up to your class. I don't have this memorized. I had to go look it up. All right, so this turns out to be 2.0634 minus 1.3169, which is 0.74648, or 0.746 if you round it off to 3. And only you know whether you're responsible for actually working that out. Okay? Let's do this one. All right. So you're going, oh, yeah. So oops, got my dx. This one's got inverse signs in it and a square root of 1 minus x squared in it as well. That's interesting. Okay, so let's go back up in here. Let's look at, oh, look, this one right here. There's that inverse sign, and you'll notice that its derivative is that 1 over 1 minus x squared. That might be kind of handy. All the way down here. Okay, so if u is equal to the inverse sine of x, then du is 1 over the square root of 1 minus x squared. All right, so this is actually not too bad, huh? So you have 0 to the 1/2, and you'd have, this is the inverse sine of x times 1 over the square root of 1 minus x squared dx. And this is your du, right? So this is u du. Hey, that's not too bad, right? Now, again, if you're going to sit here and carry on these 1/2s and this 0 and everything, keep in mind that these are x values. And you cannot just substitute those into u right now. Now, you can go through and change those x's to u values, right? But let's not, okay? So to integrate this one, you would then have u squared over 2. But u was the inverse sine of x squared over 2, right? And you're going to integrate from 0 to 1/2. So this is 1/2. And you'd have the inverse sine of 1/2, whatever that is, squared, minus the inverse sine of 0, whatever that is, squared, all times 1/2. So this is 1/2 pi over 6 squared minus 0 squared. So this is 1/2 times pi over 36. So it's, I'm sorry, pi squared over 36. So it's pi squared over 72, which is exact. And like I said, it's kind of like, okay, it's not ringing a bell with me about what kind of size that is, other than this is like 3.14 squared. So if that was squared, that'd be kind of close, give or take, to 9 over 72. So maybe it's not an eighth, okay, because this is 9 and a bunch of other stuff. So, it's about an eighth. All right, so it's a small number. But I don't know about you, but when I get these exact numbers, I'm always kind of going, well, is that a big number or a small number? I don't know what I just found. All right. How are you doing? Okay, one more. I swear. It's the last one. All right, so if you want to go from minus 10 to 10 of the hyperbolic cosine. All right. So the hyperbolic cosine, where does it come from? Because remember, that's the derivative of something. Here we go. So what did you take the derivative of to get the hyperbolic cosine? That would be the hyperbolic sine. See it way up here? Okay, all the way down here. But it's not just an x. So u is x over 5. So du with respect to x is 1/5. All right. So what I want is minus 10 to 10. And I just need a 1/5 right here. So I need to undo it with this 5 that's out there. Right, those are new. So I have 5. What did you integrate this to? The hyperbolic sine, because this is my u, and this is my du. So hyperbolic sine of u from minus 10 to 10, but remember these are x values. So I have to switch it back. So this is 5 hyperbolic sine, switch it back to x is u is x over 5. So this is 5 hyperbolic sine of 10 over 5 minus the hyperbolic sine of minus 10 over 5. And there are some little trig properties for this. So this is the hyperbolic sine of 2, but this minus comes out and then multiplies that one. So you'd have plus hyperbolic sine of 2 again. So I have 2 of those. So I've got 5 times 2 hyperbolic sine of 2. So this is 10 hyperbolic sine of 2. And this is the exact answer. But if your teacher or the whatever you're doing your homework with wants you to approximate it, the hyperbolic sine is also represented like this. So the hyperbolic sine of 2 would be e to the second minus e to the minus 2 over 2. And this turns out to be 3.6268. So you would have 10 times 3.6268. So that's give or take 36.27. Give or take. Okay? Now, so this is the end of the definite integrals. There will be a worksheet for you to try some of these problems. That the link is in the description down below the video. The next video is going to round up about the average or mean value for an integral, and then we'll talk about areas, and then that will constitute the pretty much all the topics that are in a typical Calc 1 class, and you'll have seen everything, and then probably some, because a lot of Calc 1 classes don't have these hyperbolics and inverse trig functions in there. And then y'all will be ready for Calc 2. Okay? All right.